Well, welcome back. Here is class number 6 in ME370, Elements of Mechanical Design. And we're going to talk about strain today. Okay, so we want to refresh ourselves about the stress-strain relationships, talk about things we call the constitutive equations, and then I want to do strain transformation. Right, so that's going to be an interesting and important thing to know about, to know its existence of, and a good thing to know how to do. You may run across this in your engineering career, so I think it also ties in some of the concepts that we're working on. So I asked this question, how are stress and strain related to each other? And so the answer to this open-ended pedagogical question here is, well, they're related to each other by a machine, really, a pull machine. Let's see if we could find a picture of one, right? So we could call it a tensile test machine, right? So we to do a little Googling of this thing, and you'll see we'll have some machine along these lines. You probably did this in mechanics of materials or excuse me, material science class. You'll have some type of machine that will pull the thing, and it knows how much force is being applied, and it measures how much displacement. And so what we're left with is by taking the by calculating this force and dividing it by the area and taking the amount of deflection and dividing it by the original length, we're able to come up with this relationship right here. The simplest answer, though, maybe for this area, how are stress and strain related, could probably just focus in on this one part of this graph. That part where it's a nice straight line, right, that's taking place. Let me adjust this light because I'm getting a big shadow on top of my hand right here. I guess, I don't know how I'm going to do that. We'll just leave it for now. Okay. So anyway, so in this straight line area, in this linear portion of this, that's really indicative of steel more than most other materials. Many other materials don't really have that straight line part, but we will pretend that they do most of the time. And we'll say in that location, we have this relationship right here, which is also called Hooke's law. And it takes this elastic modulus right here. That's really the slope, right, of this stress-strain curve in the linear elastic region right there. So that's the slope that's taking place right there. And this elastic modulus, this slope is also called Young's modulus, if you want to remember that. And taking a little tour of this as a refresher, we note that we have this marked thing called the PL. That's the actually, I think this is the elastic limit. I'm trying to remember what that PL, I think it may be the, not the plastic limit, proportional limit. That's what they're saying, the proportional limit. To me, that's really being nitpicky there. I don't know that I would actually zoom in and worry too much about those. Those are kind of hard to tell apart. We do have the yield strength, which is interestingly enough taken by way of taking a parallel line right here at this at an offset in a strain, right? Remembering that strain, basic strain, is equal to the del, the deformation over the original length. Right there, right? So, but we take this, and it's usually going to, its units are like inches per inches or millimeters per millimeter, and you can even think of this as a percentage. I think it's a 0.02. I'd have to look it up. Offset, where we take a parallel line to this, and we see where it intersects with the curve, and that's how we define what the yield strength is going to be. We also have, in this case, we have a place where it has the ultimate strength, and then we have the fracture strength right here. So fracture occurs right here, but this is like the largest stress that it can withstand. right? And sometimes this ultimate stress, this U right here, is also called tensile strength, right? A lot of times that's because the strength might be different in compression than in tension. We'll get to that. We'll cover that. And when we get to brittle materials, and we'll see that there are a lot of times with some brittle materials, especially cast iron, there will be a different strength in compression as in tension. So when we're talking about this tensile pull test right here, we could use interchangeably this ultimate strength and the tensile strength, or sometimes this is called SUT right there. They'll be specific to that. And you'll notice that fracture happens below ultimate. We'll go ahead and mention why that is. Because this is what we call engineering stress and strain, and it's not real engineering stress and strain. You'll notice that that area is the A0. So what we're doing is we're taking the force, the P, and we're dividing it by the original area. But because of necking that's taking place, the actual stress that takes place is this one right here, as we start to see. And we can see that fracture is above ultimate right here. The same thing is actually true for the strain. We might use the length of the thing. We might want to update what that length is as we're taking data and we're coming along, and it won't be stretched out nearly as far because the actual strain that was taking place in between two different things isn't necessarily going to be based on that original length right there. But this guy is for that curve. Now, I ask an important thing. I think it's important thing to keep in mind when looking at these curves right here, that there's a physical, I guess there's an engineering property that it can be gathered by what's happening as the area underneath these curves right here, right? So we could draw a straight line down there. I meant to be straight line. And we could say, what is that? What does that represent? And you could actually answer with a couple different things. But the main thing I would say is it's strain energy. And we're going to repeat that and look at that again. That's a good concept to have in there, but it's also something called toughness. And the more area underneath this curve, the more strain energy this material can absorb. And by the way, it's strain energy per unit volume. And if you worked out the units, and I think we might do that at some point, work out what the units are of that area underneath the thing, just to give you a sense of like, what does that actually mean? So you can see that really ends up being you can understand the definitions between a ductile material. A ductile material can take a lot of strain energy compared to a brittle material of the same strength. Brittle material right there is not as tough. It doesn't absorb it because it doesn't have a lot of strain. It doesn't have a whole lot of strain before failure onto the thing. So that's a really important thing. So there's engineering stress and strain, and there's true engineering stress and strain. We usually stick with the engineering stress and strain for our for much of our when we deal with these curves. We usually stick with those. I think that's enough of a review. There's a lot of other things that we could gather from this that we might want to know, but the really important things for us is this yield strength, this ultimate strength, and that we have this linear relationship, E, the Young's modulus, that relates stress to strain. Right? They're tied to each other by a material property that's stress and strain. I'd also mention another thing, and we can think conceptually. We can think of elastic modulus as being similar to stiffness, right? And I will repeat that in another class that comes up. But that's something. So a lot of this is review, but also trying to get those synapses reconnected, because we're going to use this stuff for something useful. We're going to use it for something useful. Does that make sense? All right. So in section 3.8 in the text. Okay, that was actually out of, we didn't really deal with chapter 2 in Shigley. It has more material stuff in there, and we might refer back to those stuff. We're back in chapter 3 here, and we have elastic strain, which we remember in the x direction would be del x divided by, and I guess I decided to go lowercase l for some reason, right? So we have the original length of whatever we have, and then we have the displacement, right? So we have most of the time when doing this, we look at what the original little cube is going to be, and I say, well, we have a del x divided by 2 and a del x divided by 2 if we've stretched this thing with our f, right? That's happening onto the thing, and this has an area that's right here, and maybe it has this. Well, actually, the area is, if we're doing engineering one, would actually be this area right there, and this one here would be the original length in the x direction. Now, you might recall that and from this picture that I made, you could see that not only does it strain in that direction, but it also kind of strains in this direction too, right? It also has, now it's gotten smaller, because you can even think of I think sometimes it's not exactly true, but the volume has to kind of stay the same. So you're pulling it in one direction, so it has to shrink in another. And we know that relationship is something called Poisson's ratio. And I always think poison for some ratio, not ration. Spelling is not a strong suit of we engineers, right? And Poisson's ratio can be defined as being the negative del y divided by del x, or negative del z divided by del x, right? So the deformation here in this direction causes a deformation over here. Let's say this is the not d, but a del for the displacement del y, right? And you could even say that it's in the other direction, but it's going to get crowded right in there. Maybe I'll put it in there. Del y, del z. And that's actually del z divided by 2, because I decided to make this thing in the center as opposed to over onto one side. So a relationship that we can get is that, if we take the thing that Hooke's law, we can reverse Hooke's law and say in the x direction we have this. That's only for uniaxial stress. For uniaxial loading. Let's say uniaxial loading, if it's only in one direction, only one force being placed onto the thing, we will have this simple relationship. And then for those other directions, we'll say that the strain epsilon y epsilon z is going to be equal to mu, or is it nu? It's nu, not mu, right? Sigma x divided by elastic modulus, right? So those are like fundamental, important things to keep in mind when trying to relate stress and strain together. In the case of just normal stress, we get normal strain in uniaxial direction. That's one direction. Now, if you have shear strain, instead of being an elongation is a distortion, right? And you could see that it actually has like a little slope going on here. And that slope is what we call gamma xy, right? It's going to be that angle. And we can say that it's, we can say angle and we can say slope. They're kind of interchangeable when you get to really small angular displacements. As long as you're measuring in radians, they become really close to each other. So the shear version of Hooke's law, something we want to remember, is tau xy is equal to g gamma xy, right there, right? So, and this g is the modulus of rigidity, which I always thought was a really cool name, modulus of rigidity. As opposed to this is the modulus of elasticity, this is the modulus of rigidity. And note that sometimes some books, right, just to you might run across this, they might call this guy XX, and they would call this YY and ZZ, and then this guy in some books, right? So, AKA some books call this. So then they call another one that's kind of related, they call epsilon XY. But in that case, just so you know, it's actually going to be 2 times gamma XY, right? It's not actually equal to the slope. It's equal to 2 times this slope, right? And you could pick it around, but these are all good things to kind of know of their existence. But for the things that I've blocked out right here, those are important things to know. And there's also something of interest is that tau YZ or tau XZ is not affected, right? And neither is gamma XY, gamma XZ, gamma YZ. They're not affected by what happens in the XY shear direction. Not like the normal stresses and strains are, right? So we have Poisson's ratio for normal stresses and strains, but there is no equivalent thing taking place in shear, right? So moving on. Okay, so here's where I decided to introduce stiffness, right? So we're to you, right, and say the idea of stiffness, and just not a proof, but just a demonstration that elastic modulus is really this a similar thing, or we can think of it as being stiffness. I'm trying to get this thing to let's see, is it gonna focus? There you go. I'm sorry about that. All right. So how is elastic modulus related to stiffness? An easy thing to do is to take the simple case of the of just a simple cylinder that's being pulled by a force F, and it has an area A. And if you apply that, you're going to have a deformation del right there, and let's say that this is original length L. So what you say is we're going to have a stress that's going to be equal to F over A, and we're going to have a strain that's equal to del over L. And we know that these two are related to each other by Hooke's law, right? Those things are related to each other. So we can just put those back into place, right? We could say F over A is equal to E times del over L, right? We just substitute this in for that in for that. Well, we know that we could define stiffness as being the force divided by the displacement, right? So that's just for a spring, right? If you want to find if you want to find the force that's required, you know, is it F is equal to K del, right? That's what that is on a force versus displacement curve. K is the slope for a spring, any spring. Well, you know, a linear spring. So we know that this is true. So we could just rearrange this right here with the F and the del. And what we find then is that K is going to be AE over L, right? Just this A and this E, and it's over L. I made this capital L, but we could have made this capital L right there. But anyway, we know that that's stiffness right there for a rod. Note, though, that for a particular rod, you would have an area and you'd have a length. These are constants for a particular rod. So you see that stiffness and elastic modulus are really the same thing. So you could think of elastic modulus as the inherent stiffness of a material in the small displacement, below the yield strength in the elastic limit type of region. Now, I think it's good to keep that in mind when we're trying to recall these material properties and kind of in our memory of what's taking place in the stress and strain relationship. Now, if we want to go all possible directions, right? So we want to extend this uniaxial relationship for stress and strain to all directions. And I think I got this from this link right there, which is interesting. I wonder if that link is still good because that's been on there for a while. But I got these pretty pictures off of this right here. So I think I was trying to attribute where I got them. So this maybe it was the University of Colorado. So anyway, and some of this stuff is not in the book, unfortunately, right? So I think it's written in the book. Maybe I should open that up and double check so you can see what we would have as a comparison there. No, I don't have the book open. So I go to my books and open up I'll go to the 10th edition of Shigley and look this up. And maybe it'll open up soon. There you go. Okay, so this is in the basics and in chapter 3, and I think we're in strain, elastic strain. All right, so the relationships. Okay, so these relationships are the ones we're about to describe right here. So I'm about to write these down as a refresher. So I could have just shown them to you, but writing them down helps things. So we have epsilon x is equal to 1 over E, right? So far, right here, we're not saying anything different from this equation right there, right? 1 over E. But now let's combine these other, if something is happening in the other direction, right? If we have stress, we have to subtract out Poisson's ratio times sigma y and subtract out Poisson's ratio and sigma z from that. And we can write all the same things in the other direction, in the other directions. Y, 1 over E sigma y, and then minus nu sigma x minus nu sigma z. And you could see the pattern there. And we have 1 over E sigma z minus nu sigma x minus nu sigma y. Right? I think I have that right. And then if you wanted to strains, as I alluded to before, all you have to do is tau divided by G. And YZ, that was supposed to be a Y, doesn't look like a Y. Tau YZ divided by G, and then gamma XZ and tau XZ divided by G. All right, so we're good. Another thing we might want to know, also there's a relationship between these 3 material properties, right? So if you know 2 of them, you're able to find the third. So you don't always see them written out in books. So in our book, we see, so you won't always see all 3. Sometimes they'll just give you elastic modulus and Poisson's ratio. If they give you all 3, you could actually check. And this is a equation 321 in the book. Good to know. But also, a lot of times, because they don't give you elastic modulus, just do the simple algebra right here. And it's good to realize that if you have these 2, you can find this one right here. Now, I'm going to see how long this video is, because I might want to introduce the next part in a this is all somewhat, or should be somewhat, review for you. Maybe not these equations, but they're in the book. The problem is, almost always when we in real life, we can't measure stress, but we can measure strain. So what we would like to do, if we know strain is find stress, So that isn't as simple as reversing all of these. You could try it yourself, and we need to do a different equation. And I wrote it out at one point as part of notes. I think I've just uploaded it now. Let me see. Yes, I did. Okay, so this is new material right now, and how far are we into the video? I might start a new one instead. Yeah, we're too far into the video. So I'm going to start a new video, and this is the continuing story. We'll see how these turn out, right? So stay tuned.